Hey, hello everybody. The title of this section is Diagonalization and non-diagonalizability. And you saw me mention this a couple of videos ago when we started talking about eigenvalues and eigenvectors. Let's just start out with a diagonal matrix. And this is a matrix with non-zero entries only along the down right diagonal, the main diagonal we like to think about. So you could have something like A, B, C, D, and so on, but everywhere else you need to be equal to 0. Any matrix of that form, I use the letter capital D to denote these matrices, although you also see people refer to these as DAIG, and then they'll just list the entries along the diagonal, since DAIG is enough information to tell you that everything else is a 0. But you'll mostly see me use just a capital D for an arbitrary diagonal matrix. And these are really cool matrices because let's consider a couple examples. So let's just start with a nice example, -1, 2, 5, go 0, 0, 0, 0, 0, 0. It's my diagonal matrix. And let's consider twice D, or D plus itself. It's just -1, 0, 0, 0, 2, 0, 0, 0, 5, plus itself, -1, 0, 0, 0, 2, 0, 0, 0, 5. And we get -2, 0, 0, 0, 4, 0, 0, 0, 10. Well, that's not really a surprise. That's what you'd expect. But now let's go ahead and compute D squared. The square matrix, everybody, I think, realizes is a lot more complicated of an object to compute than just sums. That's because of the weirdness that exists with matrix multiplication. When we perform this, we're going to do all columns on the right and all rows on the left. That hasn't really changed. But let's look at what results. When I do the inner products, maybe this one against this one, the only terms that are non-zero are -1 squared. And if I do this one, the top one against the middle term, there are actually no terms that are non-zero. And the same for the top against the far right. There are no terms which are non-zero. This will continue anytime I'm not working on a diagonal. But once I get to a diagonal, like in the middle cases, you'll see the 2's show up in both cases. I get 2 squared, and then everything else follows through, and I get a 5 squared in the bottom. And so what happened with D squared is we just got the diagonal entries squared. So if D was diag, -1, 2, 5, and I decided to square it, that's just the diagonal of -1 squared, 2 squared, 5 squared. Or of course, as I've written it above, 1, 0, 0, 0, 4, 0, 0, 0, 25. But that just meant that not only is addition easy, of diagonal matrices, but multiplication is also easy, very easy. And in fact, what this means is that we can construct the following, which I'll actually list as a theorem, and I don't list too many theorems in this course, so you can really pay attention to what I do. If, let's say, D equals diag, and I'll just use the entries as lambda1, lambda2, and there, of course, is a reason for this, ... which you're probably already assuming what it is a diagonal matrix. And I'll write it out as an actual diagonal matrix here too. Lambda1, 0, 0, 0, lambda2, 0, 0, 0, lambda3, and some dots. So we have a diagonal matrix. Then, any polynomial, we'll say for p of x, p for polynomial, this is equal to a sum of some coefficients against some powers of x, n equals 0 to k, so we'll call it a kth degree polynomial. We have if I evaluate the polynomial on the input d, now what does that mean? That just means I'm replacing that x with a d, the diagonal matrix, d to the nth power. I'm considering those powers as matrix multiplication powers. So really we're thinking along the lines of C0 times the identity plus C1, that's just a constant, times the diagonal matrix plus another constant times the diagonal matrix squared, all the way up to some other constant times diagonal matrix to the k power. We can compute this object incredibly efficiently as the diagonal of the polynomial on each of the inputs. Or rather, written as a diagonal, the polynomial on lambda 1, 0, 0, 0, polynomial on lambda 2, 0, 0, the polynomial on lambda 3, and so on. And so that's really nice because it says you can do this with polynomials. It's such a stronger statement. All you have to do is apply polynomials to numbers. Maybe I'll make the remark here. Remark: as far as diagonal matrices are concerned, taking arbitrary sums and powers is as easy as applying those sums and powers to the entries. It's kind of like the freshman's dream, so to speak. You can just pass everything you want to do to the inside of the matrix. So let's look at some examples. So let's just compute P of the matrix 2, 0, 0, 3 when a polynomial of x is x squared plus 2x plus 1. Well, my theorem says that this is equal to the polynomial evaluated at 2, 0, polynomial evaluated at 3. Polynomial evaluated at 2 is just 2 squared plus 2 times 2 plus 1. Polynomial evaluated at 3 is going to be 3 squared plus 2 times 3 plus 1. Or in other words, I can write this as 4 plus 4 plus 1, 9, 0, 0, 9 plus 6 plus 1, 16. Let's compute negative 1, 0, 0, 5 to the fourth power. That's just immediately equal to negative 1 to the fourth power, 0, 0, 5 to the fourth power. And negative 1 to the fourth power is fairly easy because it's an even power of a negative number, so that's 1. 5 to the fourth power is a little trickier. You go from 5 to 25 to 125 to 625. And so those are just like immediately easy when you're dealing with diagonal matrices. You can imagine if I had asked for something like P of 1, 2, 3, 4, which would be 1, 2, 3, 4 squared. In other words, times itself. 1, 2, 3, 4 plus twice times 1, 2, 3, 4 plus 1 times the identity. 1, 0, 0, 1. That would take you a little bit of work. It's a lot easier to just get 9 and 16 from the beginning, but you can't when that's not diagonal. Similarly, really you would have not been happy if I asked you to compute 1, 2, 3, 4 to the fourth power, which is this collection of matrix multiplications. Nobody would want to do either of those. The first one is manageable. The second is really, really hard. Okay, so that kind of brings us into the process of diagonalization. Diagonalization, the entire title of the chapter. What if we could change this matrix, 1, 2, 3, 4, into a diagonal matrix? Because if we could, then all we have to do to take the powers is apply the powers to the diagonal. Now the answer is in a lot of cases we can. Not every case, but in a lot. In many cases, we can. The big question is how? Well, this is going to send us back to something that I haven't really covered too much, but let's go back to representations. Representations of linear maps, aka matrices. We had this notion that given a linear map L from a vector space to another vector space, W, we can compute the matrix capital M, which has a row and column entry, where I and J start at 1, and then they end at the dimension of W and the dimension of V, respectively, with Mij defined as the inner product of L against an Ej, and then against Fi, where Ej hat, J going from 1 to the dimension of V, and Fi hat, I going from 1 to the dimension of W, were orthonormal bases for V and W, respectively. And I kind of glanced over this as not being too terribly important of a statement, because most of the time when we extract a matrix, M, from a linear map, we would do something like, okay, AX plus BY plus CZ equals W, DX plus EY plus FZ equals U, and GX plus HY plus IZ equals V. If we wanted to extract the matrix, we would just look at coefficients. And we did, and we got away with that. We would say M was A, B, C, D, E, F, G, H, I. But just as with vectors and representations of vectors, this quote-unquote version of M, notice no subscripts, is really M represented according to the canonical bases. So what's happened is that when we extract the coefficients to give ourselves an M, is we're actually only considering the case when this EI or EJ and this FI were canonical. So this is specific to these two being chosen as 1, 0, 0, 0, 1, 0, 0, 0, 1. In that case, you exactly extract such an M. But this seems like maybe we wouldn't want to change a basis. Canonical seems like the right choice, but let's think about it. If we choose a different basis, then M looks different. It has to. There's no way that all of these numbers stay the same if I all of a sudden make a different choice of E and F here. Diagonalization is the process of choosing the right bases so that the representation of M is diagonal. So if we had been clever from the beginning and chosen a good collection of bases, then a lot of matrices are able to be represented as a diagonal matrix. Now, we're not going to go through this work and use this crazy theorem or this representation style to diagonalize a matrix, but it gives us an idea that we should be able to choose a different collection of bases to get a diagonal matrix out of it. So to that end, there's a notion of a change of basis transformation on matrices where you just take a matrix M, and it can always be written as one matrix, which I'm going to call capital X, and then a new matrix N, and then another matrix X, capital X inverse. So X and X inverse are matrices that sidle up alongside N and give you M, where the columns of X are the new basis vectors. Now, a lot of linear algebra courses will spend quite a bit of time on these change of bases transformations. I would love to, but we just don't have the time for it. So we're just going to use it as a tool where once I recognize that the columns of X are the new basis vectors, I can really jump into diagonalization quite quickly. So diagonalization. What if the columns of capital X are eigenvectors? That is to say, suppose M is a 3 by 3 matrix with 3 eigenvectors, x vector 1 associated to lambda 1, x vector 2 associated to lambda 2, and x vector 3 associated to lambda 3. Then, if I write this out, M equals X N X inverse, where I'm forming capital X from a collection of eigenvectors, and then some other matrix N, and then a collection of eigenvectors. I can rewrite this as just basically by taking this inverse and pulling it to the left hand side, I can rewrite this as M acting on x1, x2, x3 is equal to x1, x2, x3 against N. And M can distribute inside of here to give me mx1, mx2, mx3 equals x1, x2, x3 against N. Because these were eigenvectors, meaning mx equals lambda x, we can replace each m with lambda I, or the 1, 2, 3, lambda 1, lambda 2, lambda 3. That gives me lambda 1, x1, lambda 2, x2, lambda 3, x3, and in fact, if I decide to replace n on the right with a diagonal matrix, lambda 1, 0, 0, 0, lambda 2, 0, and 0, 0, lambda 3, I recover a true equality here. Truly equal. And that means that n is diagonal with eigenvalues along the diagonal. So this was really a wraparound way of saying that if I let capital X be a collection of eigenvectors, those are all columns, so columns are eigenvectors, then any matrix which has 3 distinct eigenvectors, any 3 by 3 matrix with 3 distinct eigenvectors, satisfies X and then a diagonal matrix, lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, X inverse. This is diagonalization. We've represented M in terms of a diagonal matrix. Okay, So everybody likes step-by-steps better. Nobody likes the theory. I realize that I like to feel, like I'm really enlightening everybody by introducing the theory, but let's go into the step-by-step. So step by step to diagonalize a matrix, if possible. Step 1, find all eigenvalue, eigenvector pairs, and let's just write them as lambda I x vector I. Because let's think about these as a set where I goes from 1 to n, let's say, size of the matrix. Step 2, you construct a matrix, capital X, from the eigenvectors. Since these are all vectors and I'm placing them in a row, they're all vectors and I'm placing them in a row, think about each of these as a column. Each vector is a column of capital X. Step 3, construct the diagonal matrix. Capital D, which is equal to diag, lambda 1, lambda 2, lambda 3, and so on. And a lot of students always ask me this question, does the order matter? And the answer is only kind of. These must be an eigenvalue, eigenvector pair. So those two need to be the same subscript, right? They came as pairs from the beginning, so they still have to be paired when you keep your order here. So that's the only part where some of these matter. These orders matter. Just make sure that you place the same pairs next to each other in the diagonal versus the matrix X. And then step 4, this is always going to be true. M equals X, D X inverse will be true. Equivalently, X inverse M X equals D will be true. So that's diagonalization. Kind of this very last step, just this representation of M as the product of 3 other matrices is what it means to diagonalize. So this is really called the diagonalization. So let's go through one example, and then we'll be done for today, and we can encounter some more in the worked exercises version. So let's do one example of diagonalization with the matrix that we encountered in the last video. This was the matrix. Let's diagonalize the matrix 3, 4, 4, 3. So step 1, find all eigenvalue, eigenvector pairs. And if you didn't watch the last video, go back and watch that other video. I can't believe you're here without watching that one. So the eigenvalue, eigenvector pairs we discovered in the last video, there was lambda equals 7 and lambda equals -1, and they were associated to the pairs associated to 1, 1, and associated to 1, -1. So if you don't believe me, go ahead and watch that other video again. I walk through it all. Step 2, we construct capital X, and maybe I should have added this up top. We should construct X inverse 2. X inverse from X. So capital X is going to just be, this is really the first vector, and that's the first eigenvalue. This is really the second vector and the second eigenvalue. So we've got x1 as a vector and x2 as a vector, which we can think about as me just placing this vector 1, 1 in there, and the other vector 1, -1 in there. And then I can drop those inner parentheses, and really my matrix is 1, 1, 1, -1. So I also need X inverse. Thankfully this is a 2x2 matrix, so let's never forget our formula. A, B, C, D inverse is 1 divided by AD minus BC, D, -B, -C, A. So you have x inverse is going to be 1 divided by AD is -1 minus BC is 1. And then we swap A and D, -1. We give negative signs to B and C, 1. So that's really a 1/2 out front, or 1 over -2 out front. 1/2, and I'll pull the negative sign inside, so go negative, 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 negative. So that's going to be x inverse. Step 3, we construct our diagonal matrix, which in this case is the diagonal of my two eigenvalues, 7 and 1, -1. This is the point at which we have to make sure that 7 was associated to this eigenvector and -1 was associated to this eigenvector. So just preserve that ordering. Don't screw up the ordering, but as long as you preserve it, you're good. You get a 7, 0, 0, -1. There's our diagonal matrix. And then in step 4, we have that 3, 4, 4, 3 is equal to x d x inverse. But let's actually write them all out. X was 1, 1, 1, -1. D is 7, 0, 0, -1. And x inverse was a 1/2, 1, 1, 1, -1. And so this entire object, right, I think a lot of students are unclear about this. This entire object is the diagonalization. It doesn't really mean much right now until we use it as a tool. We use it as a tool to make calculations easier. So that's why we go ahead and diagonalize, but in fact we use it as a tool to make calculations easier. So we'll see the tool in action later. I'll just mention that here. Diagonalization will be a tool to make calculations easier. And we'll see the tool. We'll see why in future videos. So we're not going to see it right now, but in about 2 videos, we'll see why. And you kind of got a hint right away, right? I was saying that, polynomials acting on diagonal matrices were a lot easier to compute. So these should be easier as well. Anyway, we're going to stop there for today. I'll see you in the next video. Bye.